Okay, welcome back. Our next episode, we're talking about centripetal acceleration and force. Okay, we've spoken about circular motion, horizontal circular motion. So if we think about it, we have a scenario where we have a particular mass here, which is the ball that's shown. Now, this thing starts off with some initial velocity sideways, but there's a force being applied by the string that's pulling it towards the middle. Now we know F equals ma, if I can write properly. We know that since F force is mass times acceleration, there is a mass, there is a force applied, so there will be an acceleration. And it's that acceleration that is changing that sideways velocity of the ball that makes it go around in that circular path. Okay, so today we're going to look at centripetal acceleration and centripetal force, the formulas involved there, solve some problems. So it's always physics, so there's always going to be some calculations that we're going to deal with. We're going to be, at the end of this, we're going to use some resolve vectors to calculate some centripetal force and acceleration, look at some examples, and we'll have a look at the relationships that we use in physics. These are the things that we tend to test in the data test. And there's a nice little meme at the top corner there, courtesy of Dr. Stone. All right, so where are we up to in our plan? Now, we've done most of the things in our curriculum. We have not yet looked at this formula down here, and we've not really explored that one down the bottom there around centripetal force. So we'll have concentrate on those two today. Okay, centripetal force. Notice it's written as the F with a little c next to it. So that's the force that causes an object to move in this circular path. This is the thing that also is causing an acceleration, because remember, F equals ma. So we have a Fc is our force. It's a force, so it's measured in newtons. We have a mass. We have a velocity squared and over the radius, or the distance it is away from whatever it's rotating around. So you can see that the force is related to the mass. It's related to this tangential velocity, as in the velocity at a tangent to the circle it's moving around, and obviously r being the radius of that circle. Don't forget, forces are measured in newtons. Okay, so how do we relate this to acceleration? So what I've written here is F equals ma. So the centripetal force equals the mass times the centripetal acceleration. Now, if we looked at the formula we had before, we had F equals mv squared over r. So what that clearly tells us is we can start to split up the acceleration part out of that. Just like that. So that's how we end up with this particular formula that we've got down in the box here. Don't forget, it's an acceleration, so it's in meters per second squared. And that's because the velocity is always meters per second, and the radial distance, the distance the way that you're rotating around, is always a distance, so therefore it's meters. That's our standard units. Think about the relationship here, and this is leading on to our next bit about the data test information. So the acceleration is proportional to the square of the velocity. So if you see on our little formula in our box here, ignore the 1 over r. Acceleration is proportional to velocity squared. All right, so it means if one of them goes up, the other one's going to go up 4 times bigger. So that's what the yellow star says. It's 4 times harder to go around a curve at 100 kilometers an hour than 50 kilometers an hour. So if my velocity has doubled, then my acceleration is going to be 4 times bigger. And that's what my proportionality tells us. That's what I mean by acceleration is proportional to v squared. All right, if one of them doubles, the other one's 4 times bigger because it is a squared relationship. Rightio. Data test relationships. Now, these are the things that we tend to look at when we investigate the results of experimental work. We test them in a data test. So if I look at my formula up the top here, the centripetal acceleration, v squared over r. So if I remove the v squared part, it's like I've gone the acceleration equals 1 over r times v squared. So that's how I end up with this relationship here. Acceleration is proportional to 1 over r. Now, when I graph acceleration versus radius, you end up with that inverse curve there. All right, that's how you know the inverse is related to. So it's 1 over r. When I change my x-axis there to 1 over r, I end up with a linear relationship. Every single time we draw a linear relationship, we do it because we want to find the gradient. We then want to relate the gradient back to something into our original equation. So if I go back to my equation and just rewrite it, v squared times 1 over r. It's like, that's my y variable, oops, plus c. Y equals mx plus c is the form of a linear equation. And you can see that I have on my y-axis acceleration, which is there. On my x-axis, which is this one here, I have 1 over r. Everything left in the equation is going to be the gradient. So the gradient equals v squared, which is why I wrote that there. All right. The c value is just the y-intercept, and that is just where this line intercepts the axis. You would expect that at 0 radius there would be 0 acceleration. However, it's often not quite right on there in some of our experimental work, particularly in high school. So that just ends up basically being a measure of any residual velocity, because velocity is my other variable in my equation, or just my systemic error for my whole experiment. Okay, let's manipulate a few others and see what else we can find. So that one in the grey box is one you'll need to remember for analysis of experimental work and for a data test. And here's a few more. Now, what we've done here is we've said that acceleration is proportional to radius. All right, now I just said it's proportional to 1 over radius. So how can we end up with this relationship here? Well, when I start with my force formula and the velocity formula, this velocity can be substituted into there. So it's like I'm accounting for the velocity and the period as I do this particular Prac, whatever this set of data is I'm collecting. So if I substitute that in, I end up with this little bit up on top of the fraction here. So now it's v squared, as it says up there. So everything in my equation's got to be squared. So the 2 is squared to 4, the pi is squared to pi squared, r squared, and the t period becomes t squared in my equation here. Now, from there, we can just simplify our equation down here. We've got our t squared on the bottom of the fraction there, that's why he ends up in there. The r's will cancel out, just leave me with 1 r on the top, and I still have my 4 pi squared. So, once I look at that, again, if I take out F equals ma from that, I already have my mass there, so everything must be equal to the acceleration, which is how I get this relationship here. And you can see I have an r on the top here, acceleration here, hence the acceleration is proportional to the radius when I'm accounting for things like the period and stuff like that, and the velocity. When they're graphed together like that, it's the same thing. Everything in this equation that's not one of those two variables becomes my gradient. Hence, I can solve for the period of rotation of this particular object. See how I've manipulated my data? All right, let's look at a few more. So I've got the same calculations just written here, but a few other little relationships. Centripetal force is proportional to 1 over r, and that pretty much comes from my formula up here. So you can see I've got a force, I've got r on the bottom of the fraction there. So what does that tell me? My gradient of that particular graph is going to be everything else. The gradient of a linearized graph of force versus 1 over r is going to be mv squared. Okay, this one here, period is proportional to the square root of radius. All right, now this one's a little bit weird. I know you can get that out of this relationship up here, but we're looking at this one down here. If I take my period here and I put it over the other side there, and I can put my acceleration back down underneath the fraction there, so I'm just manipulating algebra here, I'll get t squared equals 4 pi squared r over acceleration. Now, if I get rid of the squared on that, my r will become a square root, and that's how I end up with this one here. Here's a good task for you. If you take the square root of both sides, what will you end up as your gradient? And our last one, the force is proportional to 1 over t squared, comes from that simplification of that just on there. You've got the t squared on the bottom of the fraction, and that's what we get there. And same deal, if I draw a graph of force versus 1 over t squared, what am I going to get left with? Take those two variables out of this equation here, and my gradient's going to be everything else that's left. What have I got? I've got a 4 pi squared rm, radius times mass. Okay, you should remember those ones in the grey boxes understand how we derived those there, how we have the relationships, and what is the gradient that we get of those graphs. Okay, practical example. Racing car traveling around a circular track, similar to swinging a ball, that sort of thing. Remember, when we're ball on a string, there's tension in that string. Tension's a force. What's force measured in? Newtons. All right, so the vehicle is going around on a level road. So basically we can consider it going around a corner on a level road. It's basically an example of circular motion whilst it goes around that corner, assuming the radius of the corner is not changing. So what is the force that keeps the car on the track? All right, it's the same force slowing down that car in the little animation there. It's the friction with the road. It's the friction of the tyres with the road that cause the centrifugal force and hence the acceleration of this object around the corner. So friction is what provides our force. If there's a wet patch on a corner, what's going to happen? Well, the water will lubricate the surface between the tyre and the road of that little example there. Hence, it will reduce the friction and hence reduce the centrifugal force. The car won't be able to go around the corner as fast, which is what you'd notice on a wet, rainy day. So, car would tend to go in a straight line or spin out of control and not go neatly around the corner. All right. So when we think about a maximum safe speed to get around a corner, all right, it usually is some sort of average speed that is then equal to the friction with the road. So for cars with rubber tyres on a dry bitumen road, the friction is typically 70% or 0.7 of the car's weight. So if we think about that, the friction of the road, the force of friction, is usually around its weight. And what do we do to work out the weight? It's the force of gravity. And what's that one? Mass times gravity. So in this scenario, it would be 0.7 times that amount. So hence, can we calculate the maximum velocity? So in this scenario, the forces have got to balance. Note what it says there. The friction with the road has got to equal the centrifugal force for it to safely go around the corner. So we're going to have a centrifugal force that's got to be equal to the force of friction. So let's flesh that out and see what we can come up with. So centrifugal force is equal to the force of friction. Sub in my formulas. The centrifugal force is my mv squared over r, and we saw the friction was 0.7 mass times gravity. All we've done from here is start to cancel things out. You can see I've got a mass on both sides, so I can cancel those guys out. I can bring my radius from the bottom of the fraction here up to the other side here. And what I end up with is v squared is 0.7 force of gravity, g, 9.8, times the radius. Or if I get rid of the squared, square root of all that. So typically when the road's wet, this 70% of the car's weight as the friction can reduce down to 50% or less. Okay, here's another example. A car of mass, 1,500 kilos. So there's my mass, 1.5 tonne. Approaches a curve, 30 metres is our radius, and I've got a velocity. What's wrong with that velocity? That velocity is not in metres per second, so it's not in standard units. So the force of friction between the road and the tyres is 10,000 newtons. It can go around the curve safely. So let's have a look. If it's going at 80 kilometres an hour, what we want to know is that going to go around the corner? Is my force of friction going to be more than 10,000 newtons, so hence it goes around the corner, or less than 10,000 newtons, so it slides off? So in order to safely go around the corner, the centrifugal force has got to be less than the force of friction. If the centrifugal force is greater than this figure that we're given of 10,000 newtons, the car's not going to go around the corner and it's going to slide off. So written down what we know here, we've got a mass of the car, 80 kilometres an hour, we've converted to metres per second, and we've got a radius. So write that down. What do we need to find? We need to find the centrifugal force. We know a formula for centrifugal force. What do we have? We have a mass, we have a velocity, we have a radius, so we can find this. And that's what we get here. So sub in the values, what I've done here, there's our mathematical working. Plug it in your calculator and it all comes out in the wash. You can see it's 24,000 newtons is the centrifugal force. All right, so what does that tell us? Since the force here, look up here in this dull pink cloud, since the centrifugal force is greater than 10,000 newtons, the car will not safely go around the curve. it's going way too fast to go around that curve because this centripetal force required to keep it on the road is bigger than this frictional force that I'm told that we're given. So in order to do this, let's look at the extension here. How do we calculate the maximum safe velocity? Well, knowing our formula here, this thing here, this number here, the centripetal force, cannot be more than the friction, which is the 10,000 newtons we're given. So if I sub that in for him, I have a radius of the road, I have a mass of the car, solve for V, and I can work out the maximum velocity we can go around the corner. Okay, just a little bit of an extension on this one. We often deal with degrees in this, but radians are another symbol that we use. All right, notice it's written RAD like that. Now radians are just a little bit different. Whereas degrees, it's almost like if you're here and you're looking at a change in angle here, what is the change in angle from your point of view is what we tend to think of as degrees. Whereas if we think of this change as what is this distance here around the curve, that's more of a radians type scenario. Engineers tend to use it, looking at rotating shafts and things like that. It's very, very common in things like astrophysics and astronomy, where we're looking at the distances in the sky, how many radians across the sky is a particular nebula, that sort of thing, that type of deal. Okay, a bit more of an extension. Let's look at a practical example of this. So when large stars, much, much larger than our sun, so think of the solar mass of our sun, and we're talking many, many times larger than that, even 100 times larger. When those sorts of stars finish their life cycle and run out of fuel, they tend to collapse. And what we can often get is a neutron star. A really, really big star will end up forming a black hole. If it's still quite a massive star, but not quite that big, we'll end up forming what's called a neutron star. Now, so this is an older star that ran out of fuel and underwent this supernova. Now, what's going on here is we're running out of fuel, so the gravity is collapsing it, so the core is collapsing in on itself. Now, what happens is, as it collapses on itself, it actually compresses all the particles, and we end up changing all the protons and electrons and everything into neutrons. So it becomes a giant mass of neutrons. So what we're effectively driving here is a beta positive decay, where basically a proton is turned into a neutron. In doing that, it tends to produce a positron, which is a positively charged electron. It's like an antimatter version of an electron. If this comes in contact with an electron, they will annihilate each other and form like just a gamma ray, so there's no more matter there anymore. We tend to also form a electron neutrino, which is a very, very tiny particle, doesn't interact, it's not charged, and will tend to be lost to space fairly quickly. If you recall back to Unit 1 and your work on radiation, this reaction is mediated by a W positive boson, and we're going to come back to that guy again in Unit 4 when we talk about the standard model. But what's effectively happened here is all of our protons have become neutrons. The whole thing has changed into neutrons. It's a really, really unique example of a giant ball of neutrons that collapses on itself. Now, that's the beta positive decay. What's released out of this is a whole bunch of energy as our positrons annihilate, our neutrinos fly off into space, and we're just left with a giant ball of neutrons. So, now if we think about our centripetal force formula here, this force is effectively the gravity of the whole thing holding itself together. We'll look at more of that in the next section. But what's happening here is the radius is massively changing. So if my force is for the most part, give or take, constant, the radius is massively reducing a long way. So in order to account for that, the velocity must increase. So the rotational speed of this thing will increase quite significantly. All right? Mathematically, if r gets smaller, v's got to get bigger, but it's getting bigger v squared. So the rotational speed of this thing gets way, way faster. And whereas our sun takes a bit less than a month, I think it is off the top of my head, to rotate, these things can easily rotate in seconds. And we're talking things many, many times the mass of our sun. So looking at it slightly differently, here's what's going on here. We have this inner core of our really, really big star, runs out of fuel. Gravity basically collapses the whole thing onto itself. Everything in the center is just pretty much smashed down and converts everything, as you can see there. It all happens at 25% the speed of light. The whole outer layers are bounced off out into space and tend to form a nebula or a planetary disk, a planetary nebula type thing out in space, which is just a whole bunch of the matter of the star blown out into space. And we get this tiny little neutron star in the middle, which is a massively compressed mass. This original star has got to be a lot bigger for this to turn into an actual black hole. So this forming a neutron star is far more common. There are several types of neutron stars. Just to take it a step further, a pulsar is the common one. It tends to have a giant beam of radiation that comes out each side, but because this thing's rotating so fast, if that beam of radiation can be detected or sweeps across near where Earth is, we can detect it and hence detect how quickly this thing is actually rotating. A slightly different form, it gets a little bit weirder and basically forms a magnetic field, which we call a magnetar. These are much less common, but we're talking a gigantic magnetic field around this thing, 1,000 times stronger than a more normal neutron star, and a normal neutron star has a very large magnetic field. So these things are just ridiculous. And obviously, in order to make things completely ridiculous, let's just do both at once and be a magnetar and a pulsar at the same time, because why not? Anyway, there's a little bit of astronomy for you, just to take you a little bit further on where we use this stuff. Okay, so we've looked at our formulas for centrifugal acceleration and centrifugal force. We should be able to do some calculations on it now, which we're going to practice shortly. And we should recall those grey boxes that I had on there for your data test relationships. That brings us to the end of this section. So now that we've done all of our objectives there from the curriculum, time now to complete your work. We've done all our formulas, do some practice questions at the end of the chapter, do the review exercises and so on. Now, just one more thing. There's a couple of XKCD applications of this. The what if channel is actually not so bad. XKCD is a scientific cartoon, but the what if channel kind of takes things to the nth degree about, how fast could a human accelerate? How fast can a vehicle go around a bend? I think in that one they're looking at what's the absolute minimum time for a NASCAR car to get around the circular racetrack, but still be enough for a human to survive the forces of acceleration. How far can we take that? And this relates to an angular motion, how fast the Earth's actually rotating. And there's a nice little article there about how the days on Earth are actually changing. And this is largely happening due to things like the tides and the water sloshing around the Earth and so on, and the pull of the moon that actually is affecting how quick the Earth's rotating. Alrighty, do some practice, and I'll see you next episode. Thanks a lot.